We've already had a brief introduction on how to name alkanes, some basic IUPAC rules, methane, ethane, propane, and so on. Let's take a look at some more complex alkanes and cycloalkanes and a variety of other functional groups we'll encounter. If we have a ring in a compound, we call those cycloalkanes, and we simply take the name of that alkane and we put the prefix cyclo before it to indicate that those carbons are forming a ring. And if there's a single group that's attached, if it's a monosubstituted ring, then we assume that the point of attachment is carbon number 1, define it as carbon number 1. Because when we have a carbon chain, we have to decide which end to number from, but when the carbons are in a ring, any carbon within the ring can be carbon number 1. So we have to decide which one to assign as number 1. So for this first example, we have a 5-membered ring. A 5-carbon alkane is called pentane. So this is called cyclopentane. And then we take it, that's our parent, and then we alphabetize and number our substituents as usual and put them out front. We have a 2-carbon chain here. So that's an ethyl group. So this is simply called ethyl cyclopentane, all one word. There's no number that needs to be drawn because any place you put the ethyl on that ring, you're going to get the same compound. So this is called ethyl cyclopentane. Now, if we have 2 or more groups, now we have to decide which carbon is defined as carbon number 1. Now, if there's 1 carbon with 2 groups on there, then that would be the best place to assign as number 1, because then we would have 2 groups at position 1. And remember, we always want to get the lowest possible numbers that we can. So we'll define that as carbon number 1, and now we have to decide, are we going to number in a clockwise fashion or counterclockwise? And we want to number in the direction closest to the next substituent so that that substituent gets as low a number as possible. So let's number here in a counterclockwise direction, 2, 3, 4, 5, 6. So this is a cyclohexane parent. Cyclohexane. We have a fluoro and a methyl, and then this group is a little more complex than a simple methyl, ethyl, propyl, that sort of thing. So how would we name that? And we have some instructions here. To name a complex substituent, we need to define the point of attachment to the parent as carbon number 1, and then we perform a second, kind of like a little mini IUPAC, to describe the name of that complex group. So for example, this is the group this is the point of attachment. So this has to be described as carbon number 1 for the substituent. And then we ask, what is the longest carbon chain from that point on? And we see that we can have a 3-carbon chain here. So this is actually a propyl group, but it's more than just a propyl, right? What does it have on carbon 1? It has a methyl group. So we're going to describe this as this whole group is described as a 1-methyl propyl. So that's how we'll handle more complex substituents. Now let's alphabetize these and list them in the proper order. The fluoro comes first, so we have a 1-fluoro. And then methyl comes before methyl propyl, just like if you look that up in the dictionary, the shorter word would come next. So we have a 1-methyl. And then at carbon 3, we have this big whole group. So what we do is we write a 3, and then in parentheses, we write this big name of the complex group. And let's see if I can not completely run out of room. We have a 1-methylpropyl cyclohexane. Okay, how about this last case? We have a 4-membered ring. We call that cyclobutane. And here we have 2 groups. And we have to decide now which one should be carbon 1. Because we could either have 1,2 or 1,2. That we would get the same set of numbers either way that we numbered it. So in that case, what we do is the carbon bearing the group that comes first alphabetically is assigned number 1. So that way the substituents are listed alphabetically and the numbers are listed in an increasing order. So what we have here is a methyl. And then this is going to be a longer word. We'll have that next. Let's make this an ethyl. So sorry. So this comes first alphabetically. We'll just change that. So this is, we'll do 1 and 2 and 3 and 4. And this is another complex substituent that we're going to have to name. So it looks like a T-butyl group. That would be kind of nice if we were allowed to use a common name. We could just describe it as a T-butyl. But an IUPAC name can't use that term. So instead we go through our rules again. So now this is carbon number 1. So what is the longest carbon chain from that point on? Well, no matter which direction you go, the most you can have is 2 carbons. So this is actually an ethyl group. But it's not just an ethyl. It has a methyl here on carbon 1 and another methyl on carbon 1. So what we're going to call this is a 1,1-dimethyl ethyl. So this is the IUPAC name for the T-butyl group. It's a 1,1-dimethyl ethyl. And where was this whole group? This whole group was on position 2. And on position 1, we had an ethyl. And we can double check, see how we alphabetized. E comes before M. When we go to alphabetize, we ignore the prefixes like di and tri. And so we have a 1-ethyl, 2, 1,1-dimethyl ethyl, cyclobutane. So we have the ring for the cyclo. We have the 4 carbons. Bit by bit, step by step, in a systematic way, we're going to build these complex names up. Now, if we have a carbon-carbon double bond in a structure, those compounds are called alkenes. And the way we're going to name them is we're going to look for the longest carbon chain, but that longest carbon chain must include both carbons of the carbon-carbon double bond. So now it's no longer just where's the longest carbon chain throughout the whole structure. Now that we have a functional group in the molecule, we need to incorporate that functional group into the parent. So the longest carbon chain must contain both carbons of the carbon-carbon double bond. And then we're going to number from the end that's closer to the carbon-carbon double bond so that the double bond will get the lowest number possible. Okay? After doing that, what we're going to do is we're going to take the A in the word alkane, methane, ethane, propane, butane, and we're going to change it to an E. And so we're going to call it an alkene instead. And we're going to put a number out front that tells the reader where the double bond starts. What's the first carbon of that carbon-carbon double bond? So we're going to call it a number alkene, or you can insert that number inside the name. This is actually kind of the preferred way for IUPAC, but I think it's a little more difficult for beginning students to look at that convention. So for example, our simplest alkene is a 2-carbon alkene. He has a common name. This is called ethylene. Ethylene is a gas that is generated by fruits in the ripening process. So ethylene is actually sprayed on fruit to help them ripen when they're picked earlier for packaging and for handling. So this is commonly known as ethylene gas, but the IUPAC name, it would be an ethane derivative because it's 2 carbons, and instead of calling it ethane, we call it ethene. So not a big difference between the common name and the IUPAC name, but the IUPAC name is ethene. So this tells the reader, that E tells the reader that there's a double bond in this molecule. In this case, I don't need to indicate where the double bond is because there's only one place for it to be, right, connecting those 2 carbons. This compound is commonly known as allyl chloride because you have a chlorine that's allylic next to a double bond. So it's known as allyl chloride, but let's do its IUPAC name. We have our 3-carbon chain is right here. That's our only possibility for our longest carbon chain. And when we go to number it, we're going to number it from the end closest to the double bond. So we'll start from this end, 1, 2, 3. And so 3 carbons means it's a propane derivative because of the double bond. We call it propene. So this is 1 propene. We're going to indicate the first carbon of the carbon-carbon double bond. So this implies that there's a double bond starting at 1 and going to 2. And what else do we have on here? We have a chloro group at carbon 3. So this is 3 chloro, 1 propene. Remember, there's dashes between numbers and letters. Sometimes we leave off the 1 in this case, and that might be implied, but it's a really good habit to leave that 1 in there. We don't want to make that assumption and then make a mistake. So this would be the best name for that. Okay, how about this case? Where's our longest carbon chain that contains both carbons of the double bond? Looks like we'll come across here, but then we'll move down in this direction because that would be a longer chain than over here. And how are we going to number it? If we numbered it from here, our double bond would start at carbon 2. If we numbered it from here, 1, 2, 3, 4, it wouldn't start till carbon number 4. So we'd rather have it be at carbon 2, 1, 2, 3, 4, 5, 6. So a 6-carbon alkene is going to be called hexene. It's a 2-hexene. And by circling off and blocking off the parent, it's very easy for me to see what other groups are attached. We still have this 2-carbon group that's called an ethyl group. So at carbon 3, we have an ethyl. How about this next case? Our longest carbon chain would be this one, but the longest carbon chain containing the carbon-carbon double bond would be down here. So we have to make sure to include that. Okay, and how long is that? 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that's an octane derivative. We're going to call this 1-octene. And at carbon 2, we have a 1, 2, 3 carbon chain. That's a 3-propyl. 3-propyl 1-octene. Now, we can incorporate a double bond into a cyclic structure as well. Now, remember, with a ring, we have to decide where to start numbering our carbon chain. So one of the double bond carbons is going to be carbon number 1. And we're going to have to number through the carbon chain and then continue on to also give the substituent the lowest possible number. So if I numbered from here 1, 2, 3, 4, 5, 6, the substituent wouldn't be until position 6. If I numbered this way, 1, 2, 3, I get the lowest number for the double bond. That has to be at carbon 1. And then I also get the substituent at the lowest number. So 4, 5, 6, this is a 6-membered ring. So we would call that cyclohexane because it's a ring. Because it has a double bond, we call it cyclohexene. Okay, and where is our group? What is this group called? The benzene ring is called a phenyl group. So we have a 3-phenyl. Cyclohexene. Now here's a case where we really don't need the number. The double bond has to be between carbons 1 and 2. That's how you define a ring. There's no other place to put the double bond, since that's our highest priority. If you want to put that in there just to be safe, that probably won't hurt if you want. Okay, and what if we have 2 double bonds? If we have 2 double bonds, we're going to indicate both numbers of where the double bonds start, and we're going to call it a diene or a triene or a tetraene and so on. So we're going to include that. We're going to put that in there. And now again, we want to give our double bonds the lowest possible number. So and I need to give both double bonds the lowest possible number. So the only way to number this to give the double bonds the lowest possible number would be as so. 1, 2, 3, 4, 5. So what do we have on carbon 5? We have a bromo. We have another 5-bromo. We're going to call that a 5,5 dibromo. A 5,5 dibromo. And then at carbon 1 and carbon 3 is where we have our double bond starting. So this is a 1,3 cyclopentadiene. Notice we stick that E back in. It would be called cyclopentene, but when we have the diene or the triene, we put the A back in just because it's easier to read that way. So it's called cyclopentadiene or hexadiene or some such thing. Okay, now another thing that we need to be concerned with double bonds is the fact that we can have stereochemistry associated with the double bond, where if we have 2 groups, remember we have like cis or trans as a relationship that those double bonds can have. Now all the examples here don't have that shown. This molecule can have cis-trans isomerism, but I haven't shown one particular stereoisomer, right? I haven't shown the geometry of this molecule. I've drawn this as a linear molecule with these bonds hanging straight down. So we wouldn't be able to tell whether which stereoisomer I was dealing with here. Okay? Now, and when you have a double bond in a ring, in a 5 or a 6-membered ring, that double bond has to be cis. Those 2 alkyl groups have to be pointing in the same direction in order for them to reach each other and form a small ring. So this must be cis. If you are looking at a 7 or fewer for small rings, let's just say, for small rings. So we don't say that it's cis cyclohexane because there's no such thing as trans cyclohexane. It would be impossible to build that. Okay, but let's take a look at some examples that do have stereochemistry involved because we're going to want to include that as part of the name. Okay, now if you have an alkene simply with two groups and two hydrogens, then we could describe those two groups as being cis or trans. So cis means they're on the same side, and trans means they're on opposite sides. So for example, we have an alkene here. Let's number from the end closest to the alkene. 1, 2, 3, 4, 5, 6. This is hexene. This is 2-hexene. But one particular stereoisomer is shown of 2-hexene where the two alkyl groups are pointing on the same side. So we're going to describe this as cis 2-hexene. We're going to put that stereochemistry all the way out in front of the name to describe the stereochemistry of the double bond. Okay, here's another example. We have this in a ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a 10-membered ring. So we'd call this a cyclodecane. If it was an alkane, because it has a double bond, we call it cyclodecene. And in this case now, we have one carbon group pointing this way and one pointing this way. Let's write the name first. Sorry. Cyclodecene. But in this case, the two carbon groups are not pointing in the same direction. They're pointing in opposite directions. If you want to look at the hydrogens to confirm that, you draw on those hydrogens for those trigonoplanar carbons. You see that, in fact, they're pointing in opposite directions. So this is an example of trans cyclodecene. If we had looked at this molecule instead, if the double bond were here, this would be an example of cis cyclodecene because those two carbon groups are pointing in the same direction. Okay, so when stereoisomers can exist, we need to look carefully at the three-dimensional picture that's shown to decide which stereoisomer it is that we're trying to name. Okay, here's another example. Now we have 3 alkenes. Let's number from here so we get the lowest numbers possible. 1, 2, 3, 4, 5, 6, 7. 7 carbons is a heptane. So when we have 3 double bonds, we call this heptatriene. And where are those 3 double bonds? They start at 1 and 3 and 6. So if it's a triene, we need to have 3 numbers out front. Right? The triene 1, 2, 3 tells us where those 3 double bonds are. Okay, and is there any stereochemistry in this problem? Well, there can't be any stereochemistry on this first or this last one because there's only one group attached. But look at this middle one. There are 2 groups attached, and what's the arrangement of those 2 groups? They're on opposite sides. This is trans. So sometimes we might miss that. If it's a line drawing and it's obviously drawn in the same side, then we might notice that it's cis. But when we leave it in its regular zigzag notation, sometimes we might miss that must actually be the trans isomer that's shown. So this is trans 1,3,6 heptatriene. I don't need to say which double bond is trans because it's the only double bond that can have stereochemistry. Okay, so if we only have 2 groups, we can use the word cis and trans. If we have more than 2 groups, the term cis and trans doesn't mean anything anymore. Cis means the 2 groups are on the same side. Trans means the 2 groups are on the opposite side. So if I have 3 groups on the alkene, the term cis and trans is now ambiguous. So we need to learn new terms to describe those stereochemistries. And the new terms we have are going to be E or Z. Okay, Z is what means the same side. So kind of like if we're similar to cis, we're going to call it Z. And E means opposite sides. Now, where do these letters come from, E and Z? They come from German words. So if you speak German, you will have no trouble remembering these rules. If you're like me and these words are not familiar to you, then you need some kind of way to remember which is E and which is Z and what do they mean. And I have a little mnemonic that I came up with that I'll share with you, see if that helps. Okay, and here's how we assign it. What we do is we look at one carbon at a time and we assign the priorities to those 2 carbons. And we're going to use the same, we're going to prioritize them based on simply their atomic number. So we are comparing a chlorine to a carbon. Chlorine has a higher atomic number, so chlorine is a higher priority than carbon. Okay, and then we go to the second carbon and we do the same ranking. Carbon versus hydrogen. Carbon wins. It's a higher priority, higher atomic number, and so that is also number 1. So we rank them 1, 2, and 1, 2, and now what we do is we compare the number 1 groups and we ask, are those number 1 groups on this same side? And if we say it with a little crazy accent, then we remember that this same side means that it's the Z stereochemistry. So in other words, since these number 1 priority groups are cis-oid to each other, we're going to describe this molecule as being the Z stereochemistry. And so we put that all the way out in front in parentheses. This is italicized, as is the cis and trans are italicized, you see when they're in print. And so this is going to be called Z2-chloro-2-butene. The other stereoisomer, if I swap the chlorine and the methyl, the chlorine and the CH3, now you see that my number 1 priority group is here and my number 1 priority group is here. Now they're transoid to each other. So we ask, are the higher priority groups on the same side? Well, they're not. So now it's the opposite of Z, it's E. So we need to remember what both of those names are. And of course, the more you work with these, the more you'll become familiar with which is which. So this would be called the E isomer. So let's just take a look at a couple quick examples here. How would we name this alkene? Longest chain that contains the double bonds is right here. And what side do we number from? 1, 2, 3, 1, 2, 3. Well, this is a case where we'd have a tie for the double bonds. So how do we break that tie? Well, now we want to consider the substituents and try and give them also the lowest possible number. So we'll number from the end closest to the first substituent, 1, 2, 3. This would be the better direction to go, the correct direction to go. Okay, so this is a 6-carbon chain. We call that hexene. The double bond starts at carbon 3, so we call this 3-hexene. And what else does it have attached? We have a methyl and a methyl and a methyl. So we group those all together. We call this a 2, 3, 4, 2, 3, 4, dash, 4 dash trimethyl. Sorry, I ran out of a little room here. 2, 3, 4 trimethyl, 3-hexene. And which isomer have we shown? Well, now again, I can't, what does the word cis mean here, or trans? It has no meaning. So we have to define it as E or Z. So what we do is we break the double bond in half. We look at 1 carbon at a time. This carbon, we're comparing a carbon and a carbon. That's a tie. So how do we break the tie? We're going to move to the next atom and so on until we find a difference. This has 3 hydrogens attached, and this has another carbon attached. So this group wins. This is number 1. This is number 2. So in other words, an ethyl beats a methyl. And over here we have, again, a tie, carbon versus carbon. But this carbon just has 3 hydrogens on it, while this carbon has 2 other carbons attached. So this is number 1, and this is number 2. So which isomer do we have here? Do we have E or Z? We compare the number 1 groups. Are they on the same side? They are not. They are on opposite sides. We call that the E stereochemistry. So that goes all the way out front. We describe this as Z. How about this last one? What's our longest carbon chain? We have to come down in this direction to find our longest carbon chain containing the 2 carbons. And we'll number from this end to give the double bond on carbon 2. So this is a pentane derivative. It's pentene. It's 2-pentene. And we also have a chloro and a methyl. Who will come first? We'll do alphabetically. 1 chloro, 3 methyl. And finally, do we have stereochemistry? We need to check every time. Is there stereochemistry in this case? There is, because we have 3 different groups on here. And if I flip these 2 groups around, it would be a different isomer. It would be a different compound. So how do we describe this isomer in its name? Well, we rank the 2 groups on carbon 3. We have a methyl and an ethyl. We've done that ranking before. The ethyl is the higher priority. And what are the 2 groups on carbon 2? We have a carbon and a hydrogen. There's just a hydrogen here. So this chlorosubstitute group is the higher priority. And here we see our 2 higher priority groups are on this same side. They are on the same side. They're cis-oid to each other, so we describe it as the Z stereochemistry. When we have a carbon-carbon triple bond in a molecule, we call it an alkyne. And we're going to very much follow the same rules we did for alkenes, except instead of replacing the A in the alkane, we're going to replace it with a Y instead of with an E. So we're going to name it as an alkyne. Once again, we have to put the number out in front or insert it in the middle to say where the triple bond is on the carbon chain. And we're going to try and give the triple bond the lowest number possible. If we had 2 or 3 or 4 alkynes, we would call it a diine or a triine or a tetraine. So let's again look at some simple examples. This is the simplest alkyne. It's called acetylene. That's another fuel. Acetylene is what's used in torches, very hot burning fuel. This is called acetylene. Its IUPAC name, since it's 2 carbons, means it's an ethane derivative. We're going to call this ethyne. We're going to call it ethyne, or acetylene is another name that you should be familiar with. The word propargyl means next to a triple bond, just like we use the word allylic to mean next to a double bond. Propargyl means it's next to a triple bond, so this could commonly be known as propargyl bromide, but let's do its IUPAC. We have a 3-carbon chain in this case, numbering to give the triple bond the lowest number. This is a propyne derivative. It's 1-propyne. And at carbon 3, we have a bromine. We're going to call it 3-bromo. 3-bromo, 1-propyne. How about this case? What's our longest carbon chain? Longest carbon chain will go here, and don't be fooled by this CH3 group. I'm not going to stop at the end of this carbon chain because my carbon chain's not done. It extends up here. So there's actually a 1, 2, 3, 4, 5, 6 carbon chain here with a triple bond at carbon 1. So we're going to call that a 1-hexyne. A 1-hexyne. And what else do we have? We have a methyl and we have a phenyl. We have a phenyl. And so which comes first? LMNOP. Methyl comes first. So we have a 4-methyl and a 5-phenyl. So that's our hexyne. Now, if we have multiple double bonds and triple bonds, our names get pretty ugly pretty quickly. Here we can number 1, 2, 3, 4, 5, 6, 7, 8. It's an octane derivative. But we've got a double bond at 1 and 6, so it's an octadiene. Plus we have a triple bond at carbon 3. So here we have to, because we have 2 different functional groups in the same molecule, we have to break the name up and insert the number right before the suffix it's modifying. So this means I have a triple bond at carbon 3, and my diene is at carbons 1 and 6, starting at 1 and 6. Okay, or you could break up the name more completely and insert the numbers in both cases immediately before the functional group that they're representing, that they're defining. Okay, so either one of these is fine, but the one where the numbers are inserted are becoming increasingly more common. Now, if you have to make a choice between an alkene and alkyne, who gets the lower number? It's the alkene that wins. So in this case, when we look at our longest carbon chain right here, okay, we want a number from this end so that the double bond gets the lowest number possible. Okay, and then the triple bond just ends up where it ends up. So this is a 7-carbon chain. What do we call that? That's a heptane derivative. But now we have a ene and an ine. So let's break up the name. We have a hept2ene and then a 6-ine. Hep2ene 6-ine. And we also have a phenyl group here on 7. So we can throw in a 7-phenyl, and then that continues all one word, hept2ene 6-ine. If you have an OH on a carbon chain, we're going to describe that molecule as an alcohol, and that's going to define the parent chain is going to be the carbon containing that, the chain which contains the carbon bearing the OH group, and it's going to be named as an alcohol. So we'll find the longest carbon chain that has the alcohol attached to it. and we're going to number from the end closest that chain to that alcohol so that that alcohol gets the lowest possible number. Okay? And what we're going to do is we're going to drop the E at the end of the name, and we're going to add a new suffix. We're going to put the OL at the end of it. So it's going to be called methanol, ethanol, propanol, and so on. We need to also put a number out in front to tell the reader where along the carbon chain that OH group resides. Okay? And once again, you can sometimes see the number inserted immediately preceding the suffix so that it's no question where to what the number refers. Okay, so for example, this looks like the isopropyl group, right? When we have 3 carbons and attached at the middle. So this is called isopropyl alcohol. You may have heard of that compound that's used as rubbing alcohol. It's an astringent. You can use that as a cleaning agent. You might find that in your medicine cabinet for facial cleaners and such. So isopropyl alcohol, that's the common name for this. Its IUPAC name would follow the rules described above. So longest carbon chain containing the OH group. Okay, so the OH defines our parent. Doesn't matter in this case which way we number it because both of them would put the carbon bearing the OH as the carbon 2. So we're going to call this 2, instead of propane, it's propanol. Propanol. So we dropped the E and we replaced it with an OL. And so the number 2 tells us where that alcohol is, where that hydroxyl group, that OH group is. Okay, here's another example. We have a 4-carbon chain. Now we'd have to number it in this direction to give the OH the lowest possible number. So this is called it's 4 carbons, so it's called 2-butanol. Okay, but this also has a common name. What's this arrangement look like when we have a 4-carbon chain and we've attached something at the second carbon, the secondary carbon? We call this sec-butyl. So this could also be called sec-butyl alcohol. Those common names just give us a picture so quickly that it's really useful to be familiar with them. Okay, how about this case? We have a couple OHs, so this is where we're going to now call it a diol. And so our longest carbon chain must contain both OHs. Once we find an OH on our structure, we have to, that defines our parent carbon chain. So it's no longer just about finding the longest carbon chain. That's if all we have is an alkane. Okay, so let's go up here. Looks like that's the longest carbon chain that contains our 2 OHs. And we'll number it to give to the end closest to the first OH. So we'll number down here 1, 2, 3, 4, 5 so that we have an OH at carbon 1. So let's see, a 5-carbon alkane is called pentane. And with 1 OH, we'd call it pentanol. With 2 H's, we call it pentane diol. Notice we add the E back in. We actually add the E back in because it's easier to read that way than just saying pentanediol. That would be difficult. So it's called pentane diol. We have to tell everyone where these OHs are. They were at 1 and 4. So these numbers tell us where to find the OHs. And what else do I have on this chain? I have a 3-methyl, and I have a 1, 2, 3, 4, 5, 6. I have a hexyl. So that comes first. We have a 2-hexyl and a 3-methyl. 1,4-pentane diol. Now, once I see an OH on our chain, that's going to have the highest priority number. I no longer care where the double bond or triple bond is. I always want to make sure my OH gets the lowest possible number. So for example, in this ring, since any carbon can be carbon 1, we have to decide which is carbon 1. It's the carbon bearing the OH that must be carbon 1. And then we're going to number, again, either clockwise or counterclockwise to take care of the rest of the functional groups. So, of course, now we'll number in a counterclockwise direction so that the double bond gets the lowest possible number. So this molecule is called 2-cyclohexene-1-ol. So the 2 refers to the double bond, and the 1 refers to the OH group. Now again, when you have 2 functional groups with numbers on them, it's sometimes a little clearer to break up the name and insert both numbers directly into the name. But you clearly have to break it up a little bit, otherwise you can't just put the 2 and the 1 out in the front because then you wouldn't know which number describes which functional group. So we have to break up the name at least this much and you insert a number immediately before the suffix. Okay, how about this next one? Longest carbon chain is right here. And then how do we number it? Which end do we number it from? I don't care what number the triple bond gets. I care instead what number the OH gets. So I'm going to number from this direction. 1, 2, 3, 4, 5. And so let's say five carbons would be a pentane. The triple bond makes it a pentyne. Pentyne. So this is where the triple bond changes this middle letter. And because of the OH, we call it an pentyne-all. And let's put the 2 in here so we know where that alcohol group is. So, and the triple bond was at carbon 4. So this is 4-pentyne-2-all. Or you could say pent-4-ine. So the triple bond is starts at carbon 4, 2-all. Okay, the suffix always goes at the end. The OL is always the very last thing that you have. And we take care of all this parent stuff, and then we list out front everything else that's attached. So we've already handled the OH. We've already handled the triple bond. The only thing left is this methyl group at carbon 2. So we alphabetize all those, put them out in front. So notice how we keep building on these systematic IUPAC rules. So it's really important to get that foundation down of your alkanes and then gradually build on them with each new functional group so that you can see how they work together when you have multiple function groups in the same structure. Now, if you have an ether in your compound, an ether means that we have an oxygen attached to 2 carbons. Okay, and an ether is not something that changes the parent name like an alcohol does. We're not going to learn a new suffix for it. Okay, instead, it's simply a substituent that you might find attached to the parent. So it's just a group. How do we name that group? Okay, so if we have an OR group hanging off of a parent, normally we would call that R group have a YL ending, like a methyl ethyl propyl. Okay, what we're going to do is we're going to change that YL and we're going to make it oxy instead. So instead of ethyl, we have ethoxy. So we have ethoxy, propoxy, butoxy, and so on. If we have very simple ethers, sometimes we just use common names by listing the 2 alkyl groups on either side. So again, it's nice to be familiar with the common names, but that's not IUPAC. So for example, this could be named isobutyl ethyl ether as a common name because it has an isobutyl on one side, has an ethyl on the other side. So that is one name for this ether, but let's see how we would do it by IUPAC. Now with an ether, what we have to decide is of the 2 alkyl groups on either side, or the 2 carbon chains on either side of the oxygen, which one is going to be the parent. So we're going to look for either one that has a functional group on it or one that's a longer carbon chain here. They're both just alkanes, so we'll go on this side with the longest carbon chain. So here's our longest carbon chain, and now it's an alkane, so we treat it like any alkane. We're going to number it so that the substituents get the lowest possible number, so we'll number from this end, 1, 2, 3. So this is a propane derivative. Okay, and what does that propane have on it? It has a methyl, and then this group, what do we call this group? It's got 1, 2 carbons plus an oxygen. So we're going to call that an ethoxy group. This is an ethoxy group. And then we alphabetize it just as usual. Ethoxy comes before methyl. So we have a 1 ethoxy, 2 methyl. Okay, pretty complicated name for this molecule, so you can see why we might prefer to just call it isobutyl methyl ether because isobutyl ethyl ether because that gives a much quicker picture to those who are familiar with those common names. Okay, how about this guy? Oh, I think I'm sorry, I skipped some information on that previous slide. It pointed out that these aromatic groups, the benzene with an OH is called phenol. So this parent could be named as phenol, and the OH is defined as carbon number 1. So in the 3 position, we have a methoxy group. So this is called 3-methoxy phenol. This compound is called diethyl ether as its common name. Again, just 2 ethyl groups attached to an oxygen. So that's usually how we describe this molecule, but what would its IUPAC name be? Well, you have to pick one of those ethyl groups to be your parent, So it's no longer an ethyl group, it's now ethane as your parent. And what does that ethane have attached to it? It has an ethoxy group. Ethoxyethane. Okay, now what if we have an OH and an ether again? How do we decide who has priority and where do we go for the parent chain? Now again, as soon as you see that OH, that means your molecule is an alcohol and the carbon attached to that OH has to be your parent. So let's define that as our parent. There's our carbon chain containing the OH group. And so we'll number it from this direction to give the OH the lowest possible number. So this is a 3-hexanol. 3-hexanol because it has an OH group. And what are we going to call this group? Now again, this is not a simple methyl ethyl propyl. So what we need to do is we need to figure out how to name this. What we're going to do is our little mini IUPAC here. Remember, by definition, the point of attachment to the parent must be defined as carbon number 1. And so we number from there, 1, 2, 3, 4. So this would be a butyl group, but it's just not a butyl group. It's got a 2-methyl, so it would be called 2-methyl-butyl, but it's not a 2-methyl-butyl because we also have this oxygen. So it's going to be called 2-methyl-butoxy. It's a 2-methyl-butoxy group. So without this, it would just be a butoxy, but now we have a 2-methyl-butoxy. We put that all in parentheses, and where is that entire group attached to the parent? To carbon 5. Step by step, we'll build up these names. Okay, last case here, we have a triple bond, so that's going to define our parent. Any functional group that modifies the parent name. So, instead of having ethane, now you have ethanol or ethene or ethyne. So anything that modifies the name of the parent, a double bond or a triple bond or an OH group, that's going to be your higher priority compared to any other ordinary substituent that you have. So this is an alkyne. We're going to name it as such. We'll number from here to give it the lowest number possible. And so a 4-carbon alkyne is called butyne. So this is 1-butyne. And what do we have attached here at carbon 3? If this oxygen weren't here, we would call this cyclopentane group, we would call it a cyclopentyl group. Right? If it's just 5 straight chain carbon, we call it pentyl. So now it's called cyclopentyl, and now with the oxygen, we call it cyclopentoxy. Cyclopentoxy. Where is the cyclopentoxy? Carbon 3. 3-cyclopentoxy, 1-butyne. If we have a nitrogen-containing compound, we call those amines. And as usual, we're going to find our parent chain that contains the nitrogen. We're going to drop the E at the end of the name. We're going to add a new suffix. We're going to add the word amine as our suffix. So it's going to be named as an alkanamine, ethanamine, propanamine, butanamine, so on. Okay? Now, it's possible for a nitrogen to have more than one alkyl group. So one of those alkyl groups is going to be the parent. The other alkyl groups would be described as substituents. And because they're attached to the nitrogen rather than a carbon chain, we don't give the number of the carbon. We just list a capital N to indicate where it's being substituted. Okay? Again, we'll find some common names that if it's a simple alkyl group, we'll just call it an alkylamine. We'll see some examples of that. And we'll also see some examples where maybe it's not the highest priority functional group. So for example, this amine has four carbons in a straight chain, so it would just be called butylamine or N-butylamine. That would be a common name for that. Okay, but its IUPAC would be longest carbon chain 1, 2, 3, 4. So it's a butane derivative. At carbon 1, we have an amino group. We have a nitrogen group. So this is called 1-butanamine. We've dropped the E of butane and we've replaced it with the word amine. 1-butanamine. Now this next one, we have 2 alkyl groups. So one of them is going to be the parent. We'll pick the longer one. So this is our parent, 1, 2, 3, to give the nitrogen the lowest possible number. And so this is propanamine. This is one propanamine. But it's not just propanamine because it has, on the nitrogen, it has an ethyl group attached. So the way we're going to describe that is with the letter N, N-ethyl, 1-propanamine. So just like a number refers to one of the carbons in the carbon chain, a capital letter N, it's italicized, refers to the nitrogen in the compound as the location of the substituent. When an NH2 is on a benzene ring, we call that molecule aniline. So we could use that as a parent name, and you might come across that, that name. The NH3 all by itself is called ammonia. So it's not really an organic molecule. It has no carbons in there, but we'll see ammonia a lot. You should be familiar with that name. And let's see a few more examples. This is another one that has a very simple common name. How would you describe the alkyl group attached to the nitrogen in this case? It's 4 carbons arranged, attached to the middle carbon. This is the T-butyl group. So we could just call this T-butylamine as a common name, T-butylamine. But its IUPAC name, we'd have to follow the rules, find our longest carbon chain bearing the nitrogen. So that's right there. It's a 3-carbon chain, 1, 2, 3. So this would actually be propanamine. And what else does it have attached? On carbon 2, it has a methyl group. So we could call this 2-methyl-propanamine. Now, if we have an OH and an NH2, we have to decide which one is the higher priority because we can only have one suffix. We can't have an OL and an amine suffix. And so the rule is that OH is the higher priority. And so we would have the same carbon chain in both cases, but in this case now we're going to name it as an alcohol. So we want to give the OH the lowest possible number. So we'll number from this direction, 1, 2, 3, 4, 5, 6. So this is a 6-carbon alcohol we call hexanol. It's a 3-hexanol. So remember the OL ending tells us there's an OH in the molecule. And now we just simply name the NH2 group as a substituent, as a group hanging off, just like we have a methyl or a phenyl or a chloro. And what we call an NH2 group is an amino group. So we have a 5-amino, 3-hexanol, amino, just like methyl or ethyl or propyl or bromo or chloro. Okay, how about this one? Looks like we can use that aniline as the parent. Aniline. And how is this different from aniline itself? Well, it has a methyl group on the nitrogen and a methyl group on the nitrogen. And as usual, we combine the common substituents all together. Where are they? So it's a dimethyl, but they're both on nitrogen. So we're going to call this N, N, dimethyl. N dimethyl aniline. That means each methyl group is on the nitrogen. Okay, here's an example now. We have an ether and an alcohol and a nitrogen. So how do we handle this? Thus far, our highest priority group is the oxygen, the OH, alcohol. Okay, so the highest priority group is the one containing, the parent chain is the one containing the OH. Okay, and we give the OH the lowest possible number. Everyone else just gets whatever number they end up with. So this is actually a propanol, 1-propanol derivative. Okay, and what do we have attached to it? This is a 1, 2, 3 carbon chain. We'd call that a propyl, but with the oxygen we call it a propoxy. And here, if it was just a nitrogen, we would call that an amino group, but it has something else attached to it. What's attached to it? It has a phenyl attached to it. So just like IUPAC, this is not, we do a little mini IUPAC here instead of just amino. It's a phenyl amino. We don't have to locate the position of it because it's just one atom. It has to be attached to the nitrogen. Okay, so that would come first alphabetically. So we'll list that first. 2-phenylamino, and then 3-propoxy, 1-propanol. A little bit more about amines. We could describe an amine as alkyl or aryl, depending on the type of carbon group that's attached. If you have a benzene ring attached, we would call it an arylamine. Otherwise, it's an alkylamine. And we can also describe the amine as being primary, secondary, tertiary, or quaternary. And we define it by describing how many carbon groups are attached to the amine. So a primary amine, which we designate with this 1 degree sign, that means primary, means we have just one R group and then it's an NH2. Remember, nitrogen likes to have 3 bonds and a lone pair to be neutral. So because this has just one alkyl group, it's described as a primary amine. This would be methylamine, or methanamine would be the IUPAC. Okay, but if we had 2 alkyl groups attached, like 2 methyl groups here, we describe it as a secondary, so it's just an NH group. So here we see our 2 alkyl groups, so we would call this dimethylamine as the simplest name. Here's the IUPAC, you can check that, and methanamine would be its IUPAC name. Okay, tertiary is what we have when we have 3 alkyl groups or aryl groups, 3 groups attached to the nitrogen. So this is called triethylamine, would be a common name for this, and that's usually how we call it, because look how big and awful the IUPAC name is. That's called a tertiary amine, and it's even possible to have 4 bonds to nitrogen. But any nitrogen with 4 bonds is now going to be a charged nitrogen. So this is called a salt. It's called a quaternary ammonium salt. This is called tetramethyl ammonium iodide. Ammonia means we have an N+. And so it is possible to have even 4 groups on a nitrogen, but that's going to be an ionic compound. Now let's move into compounds that have carbonyls, CO double bond. The carbonyl is what we call a CO double bond, and there are many functional groups that contain carbonyls. The first one we'll talk about is an aldehyde, and an aldehyde is has the formula here RCHO. We have a carbon chain on one side and a hydrogen on the other. That's described as an aldehyde. So when we have an aldehyde, we're going to find the longest carbon chain that starts at the carbonyl, because there's a hydrogen here. The carbonyl is necessarily at the end of a carbon chain. So we start from here and we count our longest carbon chain, and the carbonyl carbon is always carbon number 1. So we don't say that it's carbon, we don't list it as carbon 1. That's the definition of an aldehyde. Okay, and what we're going to do is we're going to drop the E of the alkane name, and we're going to end the suffix Al. So it's going to be called an alkanal. The Al ending means we have an aldehyde. Notice how close that is to an OL ending we saw for the alcohol. Very important to have neat penmanship when you're doing these nomenclature problems, because the difference of a single letter can mean a right or wrong answer or a totally different structure. Okay, and as I mentioned, no number is given to indicate where the carbonyl is. So our simplest carbonyl is right here. A simplest aldehyde actually has a hydrogen on both sides. That's the simplest aldehyde. He's called formaldehyde. And if you've ever worked in a biology lab, you're familiar with formaldehyde, because this is used as a preservative for dead tissues. If you ever dissected a frog or something, that smell that's associated with that is the formaldehyde coming from that preservative solution. So this is the simplest case, just a single carbon. So that means it's a methane derivative, right? And what do we call this? We drop the E from methane and we add the letters Al. This is called methanal. Methanal means I have an aldehyde, but almost always this is called formaldehyde instead. It's such a common name. Okay? This one where we have the next simplest aldehyde has just a methyl group on one side. He's known as acetaldehyde, and we're going to see this acid common name pop up again and again and again. This acid group, or the AC group, represents a carbonyl and a methyl group attached. So a COCH3, a carbonyl with a methyl group attached. And so because this is the aldehyde derived from this acetyl group, we call this acetaldehyde. We're going to see this name pop up again and again. Okay, but that's its common name. What would its IUPAC name be? Okay, longest carbon chain, we have 2 carbons, 1, 2. And so instead of ethane, we have ethanal. Notice there's no number. We don't say 1 ethanal. That's impossible. It's just called ethanal because the carbonyl has to be at carbon number 1. Okay, here's a more complicated molecule. Here's our parent. Must number this way, 1, 2, 3, 4. So this is a butanal. Okay, and I've already shown that the carbonyl is the higher priority because that's the fact. The prioritization of functional groups is based on oxidation state. And so a carbon with 2 bonds to oxygen is going to be a higher priority than one with a 1 bond to oxygen. So carbonyls, any carbonyl is going to beat out an oxygen, be a higher priority. So we're no longer going to name this molecule as an alcohol. We're going to name this as an aldehyde. So now we have to deal with this OH group simply as a substituent. What are we going to call it? We're going to call it a hydroxy group. We're going to call it a hydroxy group. So at carbon 4, we have a hydroxy. So this is called 4-hydroxybutanol. Notice it's not hydroxyl. There's no L there. It's just hydroxy. This is benzaldehyde. The aldehyde that's derived from benzene is called benzaldehyde. What would its IUPAC be? Let's see if we can come up with that. What's our longest carbon chain containing the carbonyl? There it is, just 1 carbon. So this is actually a methanol derivative. What does it have attached? It has a phenyl group. So you could call this phenyl methanol. We wouldn't find it named that way very often, but it's important to know both the common names and the IUPAC names. A lot of times if you go to a chemical supplier catalog and you're looking it up, sometimes it's just as likely to be listed as in its IUPAC name as its common name. So it's really important to go back and forth. A lot of times you pick up a reagent bottle in the lab and it might have the common name rather than the IUPAC name. So that's why they're stressed so often, and you know, it is a short list of common names, and you do want to be familiar with them so that you can communicate properly. Okay, how about this last one? This is carbon 1, has to be part of our parent chain. This is where our parent chain starts. And we'll go like this for our longest carbon chain. We also want to include that double bond. So 1, 2, 3, 4, 5. So let's say it started out as pentane. The carbonyl at carbon 1, the aldehyde, makes it pentanal, and the double bond makes it pentenal. So we have at carbon 2, we have pentene, and then Al at the ending. Remember, there's no number for the aldehyde, so this number 2 must be referring to the location of that double bond. There's nothing else for it to mean. So 2-pentenal, and what else do we have? We have a methyl group at 3, so 3-methyl. 3-methyl-2-pentenal. Anything else for this problem? How about stereochemistry? Let's take a close look at that double bond. Is there more than one way to draw this? If I had this carbonyl down in this position, would that be the same molecule? That would be a unique molecule. So we have to show only this stereoisomer was drawn, so we have to indicate that stereochemistry as part of our name. So can we use the word cis or trans here to describe this alkene stereochemistry? No, because we have more than 2 groups on the alkene. We have to use the E and Z description. So remember, what we do is we kind of separate the 2 carbons of the alkene. Our higher priority group on carbon 3, we have a methyl versus an ethyl. Ethyl wins. On carbon 2, we have a carbonyl versus a hydrogen, so the carbonyl wins. So our higher priority groups in this case, are they on the same side? Nope, they're on opposite sides. Opposite sides means E. So this is the E stereochemistry. Now a ketone is another carbonyl containing compound, but in this case now we have an alkyl group on both sides, a carbon group on both sides of the carbonyl. That distinguishes an aldehyde, which is at the end of a carbon chain because it has a hydrogen attached, compared to a ketone. Now, what complicates things for the nomenclature of a ketone is you have a carbon chain, and that carbonyl could be anywhere along the carbon chain. So now we're back to the case where we find the longest carbon chain bearing the carbonyl carbon, and then we number it from whichever end is closest to the carbonyl so that the ketone gets the lowest possible number. What's the suffix for a ketone? We drop the E ending and we add O-N-E. So it's called an alkanone, and we have to put a number out in front or in the middle to indicate where that carbonyl is. So let's see some examples. The simplest ketone we can have is acetone. The common name is acetone. Where does the name acetone come from? Well, remember that acetyl group we had? The carbonyl with the CH3? Well, if you made that a ketone, the simplest way to make it a ketone is to add another methyl. So that's the ketone of the acetyl. We call it acetone. Acetone, of course, very commonly used solvent in organic chemistry. We use that in the lab a lot, sometimes for washing glassware, dissolving organic compounds. Awesome solvent. Nail polish remover. Most nail polishes removers are acetone based to dissolve the organic nail polish. It's also very good for dissolving organic inks and permanent inks. You could use acetone. You can use your nail polish remover to dissolve, paints and varnishes and all sorts of things like that. So it's a great organic solvent for dissolving organic things. And it's an example of a ketone because we have a carbon chain on either side of the carbonyl. And what would its IUPAC name be? Well, we have a 3-carbon chain, 1, 2, 3. So it's a propane derivative. We're going to call this propanone. And actually, you don't even need to put a number because there's only one propanone you can have. It must be on carbon 2, but we can put that in there just to be safe. It's 2-propanone. So ONE tells the world we have a carbonyl at the number given. How about this next one? Where's our longest carbon chain containing the carbonyl? So let's go this way. Number it from the end closest to the carbonyl. So we'll number this way. 1, 2, 3, 4, 5. So this is a pentane derivative. This is called pentanone. It's going to be 2-pentanone. 2-pentanone. And what else does it have attached? It has a 3-methyl and a 3-ethyl. Sometimes students get confused when they see them at the same position. They try and group them together somehow in the name, but it doesn't matter if they're the same carbon or different carbons. We list all our substituents as usual. We alphabetize them and we put them out in front. So ethyl comes first. We have a 3-ethyl. Methyl comes next. We have a 3-methyl. Very simple. No need to panic if they're attached to the same carbon. And then what if we have a ring here and a double bond? How do we incorporate all this? Now again, anytime we have a carbonyl and a ring, that carbonyl must be carbon number 1 because we're going to name it as a ketone. And now we'll number, in this case, in a clockwise direction so that the double bond also gets the lowest possible number. So let's see, 6 carbons in a ring is called cyclohexane. With the double bond, we call it cyclohexene. And with the carbonyl ketone, we call it cyclohexenone. This is cyclohexenone. So we have a 2-cyclohexene, 1-one. 2-cyclohexene. The 2 refers to the double bond. The 1 refers to the carbonyl. Of course, we can break it up completely and put the 2 right before the ene and the 1 right before the one. You'll see that pretty regularly, so you should be able to work with either of those. Remember, we don't have to say that this is cis double bond. It has to be cis in a 6-membered ring or a 5-membered ring. It's when we get to 8 or higher that we have the possibility of having cis or trans. Okay, this is another common ketone. It's nice to know a name for it. It's called benzophenone. When we have a benzene ring and a phenyl group, benzophenone is the common name. How about the IUPAC name? How about the IUPAC? We have a 1-carbon ketone. That's kind of tough to do, but that would be the IUPAC. This is a methanone derivative, and what do we have? We have 2 phenyl groups, so we would call this diphenyl methanone. Very strange name. IUPAC names end up that way sometimes. And how about this list last time? What if we have 2 ketones? Well, just like we could have a diol or a diene, we're going to call this a dione. So here's our longest carbon chain. We number it to give the carbonyl the lowest possible number. Run into the first carbonyl, we want the lowest possible number. And so 7 carbons is a heptane, and 1 carbonyl would make it heptanone. So this is going to be 2,4-heptane dione. So just like we stuck that E back in there when we did a diol, just so it's easy to read, we do the same thing anytime there's a di or tri or tetra prefix we have to put in there. So 2,4-heptane dione. And what's this group attached to carbon 6 here? What are we going to call that? Without the oxygen, we would just call this a phenyl group. So with the oxygen, we'll call it a phenoxy. At carbon 6, we have a phenoxy. If we have a benzene ring, we would name the compound with benzene as the parent. And let's take a look at some other aromatic compounds that we might encounter in our nomenclature problems. Benzene is again, as I said, would be described as a parent as benzene. But there are several heteroaromatics. These are called heteroaromatic compounds. And that means we have aromatic rings with something other than carbon, a heteroatom, nitrogen, oxygen, sulfur, something like that. And these are also aromatic compounds, and these are very common names that you should be familiar with. Benzene with a nitrogen replacing one of the carbons is called pyridine. This is called pyrrole, furan, and thiophene. Those are real common ones that are good to know. When we go to number of benzene, any of these carbons can be defined as number 1. You make that choice. Okay, but in a heteroaromatic, the heteroatom is defined as position number 1. So this would be 1, and then you number in whatever direction you want. 1, 2, 3, 4, 5, 6. So a 2-methylpyridine means that the methyl group is attached on the carbon right next to the nitrogen. And same with pyrrole oxygen. The heteroatom is always position number 1. Okay, well, you can have some fused aromatics. It's called fused when some aromatic rings share sides. So this guy is called quinoline, for example. 2 benzene rings attached to another is called naphthalene. Naphthalene is used as for moth repellent. So mothballs have the same kind of smell that naphthalene does. Very, very aromatic, actually, which is where the name kind of came from. Anthracene, when you have 3 together, and so on. There's lots. I'm just showing a few examples here. But when you have a fused aromatic, let me show you the numbering. We start with one of the carbons next to the point of fusion, and then we go around one ring, 1, 2, 3, 4, and then we jump to the next ring, 5, 6, 7, 8. We do not number. We skip the numbers for these because those carbons already have 4 bonds to carbon. There's no way you can add a substituent to those positions. So that's kind of interesting. A 1,5 dimethyl naphthalene means that we have them in this position and this position. When we have 2 benzene rings directly attached to each other, that's called a biphenyl. That's a common name is biphenyl. You may have heard of PCBs. That stands for polychlorinated biphenyls, and these were used as insecticides and such, and they have all sorts of long-lasting environmental impacts. So those have all been phased out. So PCBs are an important chemical that we're trying to mitigate in the environment. How about the IUPAC for a biphenyl, though? What would you call that? Well, one of these benzene rings would have to be the parent. You just pick one. That's our parent. So this is a benzene derivative. That's our parent. And what does that benzene have attached to it? It has a phenyl group. So phenylbenzene would be the IUPAC name. Phenylbenzene is another way to say biphenyl. And it's also nice to be familiar with these names of aromatic compounds, because a lot of times the common names for other compounds are derived from the aromatic names. So for example, this molecule looks a lot like furan, doesn't it? It has the same skeleton as furan, except we've gotten rid of both of these double bonds. So this molecule is described, has a common name. It's called tetrahydrofuran, because it's the same thing as furan, but we've added 4 hydrogens to it. So this is called tetrahydrofuran. It's abbreviated THF for short, and that's a very common solvent that's used in organic chemistry. Now, if you have substituents on the benzene ring, we can number the ring just as usual, 1, 2, 3, 4, 5, 6, and describe it that way. But if you have just 2 groups on a benzene ring, there's only 3 possible arrangements for those 2 groups. So we have common names to describe those possible relationships. If we have 2 groups that are 1, 2 to each other, meaning they're on adjacent positions, we describe that as being ortho disubstituted. So we either can put the word ortho in italics out in front, or we could just use the letter O will represent ortho, and that describes where the two groups are attached. When they're 1,3, meaning they skip over one carbon, we call that the meta arrangement. And when they're 1,4, they're opposite to each other, they're called para. And those are the only three possibilities. If I move this substituent over here now to the other side, this is meta again. And if I move it up here, it's ortho again. So ortho and meta and para are the only three possibilities. When we start getting into aromatic chemistry and learning about the reactions of benzene and benzene derivatives, we're going to be using the terms ortho, meta, para again and again. So you're going to eventually become very familiar with these. And they can be used to very easily name aromatic compounds if we could do some common names. So for example, we have a bromo and iodo here, and they are 1,3 to each other. They're meta. So we could just describe this as meta bromo iodo benzene. So benzene is the parent. I have a bromine and an iodine, and they're meta to one another. It's a flat molecule. It doesn't matter where you put the bromine, where you put the iodine. As long as you put them 1,3 to each other, you're going to end up with the same compound every time. So it's really easy nomenclature. If you want to number it and do it that way, now you have to be concerned with who gets carbon 1 and so on. And for this, we're going to do it just like we did for cycloalkane. We're going to pick the substituent with the lowest that comes first alphabetically, and we'll give that to be carbon 1. So the bromo comes first, so he would be carbon 1, and then we number to give the iodine also the lowest number. So we would call this 1-bromo 3-iodo benzene. It's a lot more complicated than just calling it meta. We call it benzoic acid. We'll see this. We'll talk about carboxylic acids in a moment on how to name those. But he's called benzoic acid, so this could be called ortho hydroxy benzoic acid. Ortho describes the relationship. So ortho, meta, and para are good to do that. Or you could call it 2-hydroxy as another possibility instead of ortho. But then when you have more than two groups, you can't use the words ortho, meta, and para anymore because those words have no meaning. Here you could say that the two methyl groups are meta to one another. You could still use it as an adjective to describe the relationship of two groups, but this molecule can no longer be described as an ortho, meta, or para molecule because there's more than two groups. So in this case, we're going to go back to our nomenclature rules where we find whoever comes first alphabetically gets the lowest number. So we have an ethyl versus a methyl, so this is number 1. And then we number either clockwise or counterclockwise depending on which will give the lowest number to the next substituent. So we'll number this way, 1, 2, 3, 4, 5, 6. So our parent is benzene. Our parent is benzene. And what substituents do we have? We have a 1-ethyl. And how do we handle our 2-methyl and our 4-methyl? We group them together and we call it 2,4-dimethyl. Okay, so naming a benzene is pretty straightforward. There's never any stereochemistry to worry about because it's a planar molecule. Every carbon can only have one substituent on there, so that kind of simplifies things. But when we get into the heteroaromatic compounds and that nomenclature, then that can expand our vocabulary a little bit. There's also a lot of common names that exist for simple compounds and simple monosubstitute benzenes, and so these are very useful to be familiar with. In fact, you may even be required to learn them. That's quite likely. Okay, so for example, methylbenzene, when we just have a methyl group on a benzene ring, that's known as toluene. Toluene is a very nice solvent that we use for organic chemistry, and it's preferred over benzene because it's not carcinogenic. So that has some uses as well in the lab. So that's called toluene. It's called phenol when you have an OH on a benzene ring. So it's a very special type of alcohol when you have an OH attached to a benzene ring. It's called phenol. Notice the OL ending is just like we have for an alcohol, but it's not called benzol. It's called phenol. And I see I have a little typo here. Sorry. This is called anisole. A little copy and paste error. It's called anisole when we have a methoxy group here instead of a methyl. It's called anisole. When we have a nitrogen, we have it's called aniline. When we have two methyl groups, those compounds are known as xylenes. And notice that this bond is kind of pointing to the middle of the ring, and that's because there's three possible places to put that second methyl. We could put it ortho or meta or para to the first methyl, and so there's three isomers of xylene that exist: orthoxylene, metaxylene, and paraxylene. So together we call these the xylenes if you maybe had a mixture of those dimethylbenzenes. And finally, it's called cresol when you have an OH and a methyl. So some of these very simply substituted benzene rings have common names. You're guaranteed to encounter them, so being familiar with them is really going to pay off. So for example, this one has a methyl and an OH, and they're para to each other, so this molecule can be called paracresol, or it could be called paramethylphenol, right? Para or maybe 4-methylphenol. Or it could even be called hydroxymethylbenzene, right? All sorts of names you can come up with for aromatic compounds. A lot of times, we get to a situation where there are more than one acceptable name. So you definitely want to check with your instructor to see what their expectations are. This is an interesting aromatic compound. It's a toluene derivative. See the word toluene in here? It's called trinitrotoluene. Here's the toluene. That means methylbenzene. And it's a derivative of that because it has these 4 nitro groups on. And guess what this is called? Trinitrotoluene. This is called TNT. So this is the structure of dynamite. So that name, when you explore that name, it comes from the common name of this aromatic derivative. Very explosive. Okay, let's take a look at carboxylic acids. This is another carbonyl-containing compound. And a carboxylic acid has this formula here. We have a carbonyl and an OH group attached. And this is no longer now an alcohol. And it's no longer a ketone or an aldehyde. This arrangement of atoms is combined together, taken as one function group called a carboxylic acid. And it'll be named as a carboxylic acid. So it must be at the end of a carbon chain because it has the oxygen stops the carbon chain. So once again, kind of like the aldehyde, the carboxylic acid defines the beginning of the carbon chain, and we number from that point onward to decide how long our parent chain is. Okay, but we never have to designate the carboxylic acid group is a carbon 1, because that's the definition. It must be. And what we're going to do is we're going to adopt the E ending of our alkane, and we're going to add two words. We're going to make the first word oic as our suffix, and then we're going to do a space and then the word acid. So we're going to have an alkanoic acid. Tells us we have a carboxylic acid. So again, a few common names here. Our simplest acid with just one carbon is known as formic acid. This has a real interesting history for this name. This is the acid that can be extracted and isolated from ants. If you take some ants and smash them up and extract the organic or the acidic component, you'll be able to isolate formic acid. And so the Latin word for ant is forma, and so this was called formic acid since it's the acid derived from ants. Again, very commonly typically called formic acid, but its IUPAC would be derived from the fact that it's just one carbon, so it's a methane derivative, but instead we drop the E ending of methane and we add the suffix oic, and then we make a space and then we put the word acid. So this is called methanoic acid. Methanoic acid means I have a one carbon carboxylic acid. So I have one carbon, and on that carbon I put a carbonyl and an OH. That's what makes it a carboxylic acid. Okay, this guy's called acetic acid. Why do we call it acetic acid? Well, there's our acetyl group, our carbonyl with the CH3. When we make it a carboxylic acid, we'll call that acetic acid. Acetic acid is actually the acidic component of vinegar. So that's what makes vinegar smell and taste that characteristic smell, and has that bite, that acidic bite. So most often we call it acetic acid. We abbreviate it ACOH, by the way. A lot of times you'll see that abbreviation, the AC group, representing the carbonyl with the CH3. And what would its IUPAC name be? What would its IUPAC name? Here we have a 1,2 carbon chain, so it's an ethane derivative. We're going to call this ethanoic acid. 2 words, ethanoic acid. How about a more complex carboxylic acid? Here's our parent. Have to start at the carbon bearing the carbonyl. So both of these functional group, both of those atoms are going to be incorporated into our parent name. 1, 2, 3, 4, 5. 5 carbon carboxylic acid is called pentanoic acid. Okay, I do not need to say 1 pentanoic acid. There's no such thing. It has to be at carbon 1. And what else do I have on carbon 4? Now we take our substituents, we alphabetize, and we put them out as front as usual. We have a 4-methyl pentanoic acid. Benzoic acid is what we call the carboxylic acid with a benzene ring attached to it. Benzoic acid, that's good to know. And we also need to know, now that we have learned about carboxylic acids, remember the priority of functional groups depends on oxidation states. So a carboxylic acid is the most oxidized we can have for a carbon chain. And so that's going to be our highest priority. That means we're going to have to find a name for any other carbonyl that's in the structure, and any hydroxy alcohol group is also going to be named as a hydroxy. So in this example, we have 3 functional groups. We have an alcohol, and we have a ketone, and we have a carboxylic acid. All 3 of those functional groups exist. Which is the one that's going to define the IUPAC name? The highest priority is the carboxylic acid. So this is our parent chain. We're going to number to give the carboxylic acid carbon 1. Okay, so this actually incorporates the carboxylic acid. If you want to circle that, that's even more clear. So this is butanoic acid. No numbering there to put in our name. This is butanoic acid. Okay, and so we know that the alcohol group is, the OH group is going to be called hydroxy. What is a carbonyl going to be called? It's not a keto group anymore, because it's not a ketone anymore. It's going to be called an oxo group. Oxo means you have a carbonyl, not oxy, oxo. So who comes first? Hydroxy comes first, so we'll list that first. 4 hydroxy, 3 oxo. And this is all one word, 3 oxo butanoic acid. So oxo is what we'll call a carbonyl. Hydroxy is what we call an OH. And both of those are lower priority than the carboxylic acid. Remember, you can only pick one suffix. And every other group then becomes named as a substituent listed out in front. So now that we know how to name a carboxylic acid, let's take a look at some related functional groups. These are called carboxylic acid derivatives because they can all be derived from a carboxylic acid. They're all related to a carboxylic acid. Okay? We can have what we're doing is we're varying the group attached to the carbonyl. A carboxylic acid had an OH, right? And we're varying the group, and what all these have in common is that each of these groups has lone pairs. A halogen, remember, X represents a halide. So a halogen has 3 lone pairs, oxygen has 2, oxygen has 2, nitrogen has 1. So you can see that the general structure for these carboxylic acid derivatives looks like this. It's got something attached to the carbonyl with a lone pair. We're going to describe this as a leaving group, and this is actually going to define the reactivity of carboxylic acid derivatives, as we're going to see that being involved in reaction mechanisms as a leaving group. We'll get to that down the road. The nitrile doesn't look a lot like a carboxylic acid, but it is related. Just like this, all of these have a carbon with 3 bonds to heteroatoms, an oxygen, and something else with a lone pair. This also has 3 bonds to a heteroatom, 3 bonds to nitrogen. So even though he looks a little different, he's also related. This is called a nitrile. It's called an amide when you have a nitrogen attached to the carbonyl. It's called an ester when you have an OR group. Okay, so it's no longer an ether. An ether means I have R, alkyl, and then an oxygen, and then an alkyl. That makes it an ether. When one of those groups is a carbonyl, we call it an ester. When both of the groups on either side of the oxygen are carbonyls, we call that an anhydride. And if we have a halogen attached to the carbonyl, we call it an acid halide. Okay, so one by one, we'll go through the nomenclature for these, but I just wanted to kind of put it in context showing you that each of these is related to the parent carboxylic acid. Because if you know how to name the parent carboxylic acid from which these are all, to which these are all related, then it's going to be a little easier to name the particular derivative we're looking at. So we'll start with an acid halide. What we'll do is we'll find the longest carbon chain that starts at the carbonyl carbon. So we have to start at the carbonyl carbon. It's always carbon number 1, so we don't even mention that, just like a carboxylic acid. And what we do is you drop the E and we add the letters O, Y, L. So we're going to get an alkanoyl halide. Then we're going to list the halide, making it an acid halide. So, for example, again, coming back to our common names, a common name for this molecule would just be called acetyl chloride. This is the acid chloride derived from acetic acid. We call it acetyl chloride. What would its IUPAC name be? We have a 2-carbon chain, 1, 2, so it's an ethane derivative. But we're going to drop the E and add O, Y, L, ethanoyl. And we make a space, this is another 2-word name, and we list whatever halogen happens to be here. It's most often chlorides that we deal with. You'll see that 9 times out of 10, but it is possible to have other halides as well. So this is called ethanoyl chloride. Again, pay very close attention to these details. If you drop the O, that name doesn't exist. If you drop the Y, then you're talking about an alcohol, and you've made a mistake. So be very careful, O, Y, L, as our ending for an acid chloride. Ethanoyl chloride. How about this one? What's our longest carbon chain? We can include the acid chloride if you want. There's our longest carbon chain. Okay, be very careful when you have a cyclic substituent that you don't include the carbon of the ring as part of your carbon chain. You can't count it for both. Here it's the group that's attached to the carbon chain. So this is a 1, 2, 3, 4 carbon chain. So what is a 4-carbon acid chloride called? It's called butanoyl space chloride. Butanoyl chloride. And what's attached to carbon 4? Well, it would be called cyclopropane if that was the parent, but as a substituent, we call it a cyclopropyl group, cyclopropyl. 4-cyclopropyl. Propyl. 4-cyclopropyl butanoyl chloride. How about this one? What is our parent carboxylic acid we have? If this were a carboxylic acid, if this were an OH, we'd call that benzoic acid. So we're going to call this benzoyl bromide. That's our parent. Kind of related to benzoic acid, we call it benzoyl bromide. And what do we have attached? We have another bromo substituent. So we could, it's in the meta relationship, so we could just call this 3-bromo benzoyl, or we could call this meta bromobenzoyl bromide. Those would both be good names for this compound. So benzoyl bromide means I have something that looks like benzoic acid, a benzene with a carboxylic acid, but it's a bromine there instead of an OH. Now, an anhydride name is also very closely related to the parent acid to which it's related. Okay? And let's just take a look at the structure of the anhydride. If you think of the anhydride structure, it kind of looks like we have 2 acid pieces that have come together. If you think of these 2 acids, what would they have to lose to result in the structure shown? Looks like we've lost the OH on one and the H on the other. So we lost H2O. If we lose H2O, these 2 carboxylic acid groups can come together and form the structure, the product shown, and that's why it's called an anhydride. You've lost water. So in the simplest case, where these 2 alkyl groups are the same, then we simply name it as the parent acid, but instead of calling it an alkanoic acid, we call it an alkanoic anhydride. So for example, this came from acetic acid. This is related to acetic acid. So we could just call it acetic anhydride as its common name. This is acetic anhydride. The abbreviation for that is AC2O. It's got 2 AC group acetyl groups attached to the middle oxygen. Okay, but what is its IUPAC name? So for the IUPAC name, let's take a look at just 1/2 and name that acid. That acid would be a 2-carbon acid, so it's an ethane derivative. This would be ethanoic acid. Ethanoic acid. So now we call this ethanoic anhydride. So we just replace the word acid with anhydride. What if it's not a symmetrical anhydride? We call those mixed anhydrides, meaning it came from 2 different acids, if you will. Then all we do is list both acid groups before the word. So what carboxylic acid did this come from? 1, 2, 3. This was a propanoic acid. And over here, this came from 1, 2, 3, 4. This came from butanoic acid. And so when we brought those 2 acids together, if we think about that as a way to come up with the IUPAC name, we just list them alphabetically. This is butanoic, propanoic anhydride. And that's so simple it seems like, that would be a common name, but that's actually how you do the IUPAC name. You just list the 2 halves to the anhydride. Now if you had a diacid like this, now again there are common names associated with most of these diacids: oxalic, maleic, succinic, glutamic, and so on. So these are, you might come across these common names, and it's going to be useful in this case. This is called succinic acid. Let's try and do the IUPAC for this one. Just see if we could do that. It's a 4-carbon chain, 1, 2, 3, 4. 1, 2, 3, 4, so it's a butane derivative. If we had just 1 carboxylic acid, we would call it butanoic acid. So because we have 2, we call this butane dioic acid. So remember, we add that E back in so we could fit the D. Butane dioic acid. Remember, oic acid is our suffix. So just like we'd have diol or dione, we could have dioic acid. So if we take succinic acid and lose water from this structure, what can happen is the 2 carboxylic acid groups can come together to form a cyclic anhydride. In fact, we're going to be seeing the mechanism of this eventually. And what we'll get is a 5-atom ring that looks like this. And that is an anhydride structure, right? You have the oxygen with a carbonyl on both sides. This is definitely an anhydride. And the way we describe this anhydride is by referring to the parent acid it came from. So this is called succinic anhydride. Succinic anhydride. And believe me, you don't want to know the IUPAC name for this. This is really how most of us refer to it, is just by its common name. So some of these cyclic anhydrides you'll see are named, their name comes from the common name of the parent diacid. Now I think esters are a little tricky to name because an ester has 2 R groups. It has the R group that's attached to the carbonyl side, and it has the R group that's attached to the oxygen side. And it's possible to mix those up when you're first learning, but let's see how we can keep them straight. And I think the way to do that is to immediately take a look at an ester structure and immediately break it down to, okay, here is the parent acid to which this ester is related, right? This kind of looks like the carboxylic acid group. This is the parent chain. This is the parent right here. And this is just an additional alkyl group that added on to make it an ester rather than a carboxylic acid. So what we're going to do is we're going to drop the suffix oic acid, and instead we're going to use the suffix O8 to tell everyone that it's an ester instead. And what we're going to do then is we're going to list in front, we're going to list the alkyl group that makes it an ester. Okay, so ultimately our name is going to be an alkyl space alkanoate. The alkyl group is this part that's attached to the oxygen. The alkanoate is our parent, just like the alkanoic acid was. Now, a lot of words. Let's just look at some examples, and I think it'll make a lot more sense. Okay, so for example, this is acetic acid. Okay, we call that acetic acid. Its IUPAC is ethanoic acid. Okay, ethanoic acid is related to this ester because we still have the components of ethanoic acid, right? We still have the 2 carbons and the carbonyl with the oxygen attached. Okay, but it's now an ester because there's an R group here. There's an alkyl group instead of a hydrogen. So instead of calling it ethanoic acid, we're going to call it ethanoate. We're going to use the suffix -ate to indicate that it's an ester. And there are a lot of ethanoate esters you can have. All sorts of different esters you can have because this alkyl group can vary. So which ester do we have in this case? We have the methyl ester. So we just list the word methyl out in front. This is methyl ethanoate. Okay, its common name for an ester would be acetate for this acetyl group as an ester. So we would call this methyl acetate. So that's a very good common name to know as well. Let's try another example. Okay, here this is an ester because we have a carbonyl with an OR group attached. How do we name it? First, we really want to identify the parent acid. Here's the carboxylic acid that's related to the ester, of which it's a derivative. And so how would you name that acid? It is a 3-carbon acid, 1, 2, 3. Right, so it's a propane derivative. You would call it propanoic acid. So we're going to name this propane ester. We're going to call it propane O8. We're going to call it propanoate. Drop the E and add O8. So it's propanoate. And which ester is it? What do we have over here? This is an ethyl group making it an ester. So we call this ethyl space propanoate. Esters are named as 2 words. Ethyl propanoate. Let's try another one. This one's a little more complex. Here's our parent ester. Our parent chain, that's because that came from the carboxylic acid. Remember, the carboxylic acid is the highest priority functional group, so that must be our parent. We're going to number from there, 1, 2, 3, 4, 5. Okay, so it was pentane that we started with originally, but we have a double bond here, so this is actually going to be called 4-pentene. 4-pentene. But it's not pentene, it's an ester. So what suffix do we use for an ester? We drop the E and we add O8. So this is called 4-pentene O8. So remember, double bonds and triple bonds we can always sneak into our name because they affect a different part of the parent name, right? They just add replace this A with an E or a Y. So we can always incorporate those in there. 4-pentenoate. The 4 must be referring to the double bond because the ester needs no number. The ester must be on carbon 1. Okay, so this is good so far. Now we ask, what is the alkyl group that's making it an ester? Okay, so we come over here. This is a little complicated now. This is a complicated group, so we just have to recall that the carbon point of attachment is defined as carbon 1. And what's our longest carbon chain? That's it. It stops right there. This is a methyl group. This is a methyl group, but it's not just methyl. What does it have attached to it? It has a phenyl group attached to it. So we're going to call this phenyl methyl. Phenyl methyl space 4-pentenoate. Okay, now phenyl methyl, I just realized was on the previous slide. I forgot to mention that with the aromatic nomenclature. This group, there's a common name for a benzene ring with an extra carbon. It's called a benzyl group. Right, the carbon next to a benzene ring is described as a benzylic position. This is called a benzyl group. So a common name for this might be benzyl 4-pentenoate. That would be the common name. But the IUPAC name is phenyl methyl space 4-pentenoate. Okay, and once we figure out how to name esters, it turns out we can use that same nomenclature to describe carboxylate salt. It's called a carboxylate when you have an RCO2 minus. RCO2 minus. So it's like a carboxylic acid that has lost a proton, has been deprotonated. We call it a carboxylate. And we use the exact same rules to name this. So again, we kind of look at the parent acid from which it's derived. This would be benzoic acid. So now we call it a benzoate with the negative charge there. This is called benzoate. And in this case, it's not an alka group that's making it the benzoate, it's a sodium. So we just list the counter ion out in front. Sodium benzoate. So you can have, you know, sodium acetate, you could have, you could have lithium pentanoate here if this was the lithium salt. And so you'll come across those names as well when you're looking at carboxylate salts, and so it's good to be familiar with that nomenclature. Amide nomenclature goes as follows. An amide is when you have a carbonyl with a nitrogen attached. So it's no longer an amine. That carbonyl now makes it an amide. Again, all the difference that a single letter makes. So once again, this must be carbon 1. We count the carbons from that point forward, find the longest carbon, starting from there. And what we do for our name is we drop the E and we add the entire word amide. So we get an alkanamide as the parent. The suffix is the entire word amide. And if we have groups attached to the nitrogen, as usual, just like we did for the amines, we'll identify those as N substituents. So again, let's look at a very simplest example. Acetamide is what we call it when we have the acetyl group that's turned into an amide. What would its IUPAC be? Well, we just have a 2-carbon chain, so that's an ethane derivative. This is an ethane derivative. We drop the E of ethane and we add the word amide. Ethanamide. Ethanamide would be the name of this compound. This guy is called N,N-dimethylformamide. Let's see if that name makes sense to us. Where does formamide come from? Well, it comes from formic acid, doesn't it? Formic acid was our simplest carboxylic acid. That's the one that came from ants. And like formaldehyde, that's where the name formaldehyde comes from, is related to formic acid. That's the aldehyde with this 1-carbon structure. So this is the 1-carbon amide, so we call that formamide. And it's N,N-dimethyl because there's 2 nitrogens on the methyl. So that's N,N-dimethylformamide is its common name. That's a good one to know because it's abbreviated DMF. This is a solvent that's used in organic chemistry, so you might see the abbreviation DMF occasionally. And how would this name change if we wanted to do IUPAC? Because formamide is not an IUPAC name. What would the IUPAC name be? This is just a 1-carbon chain, so that means it's a methane derivative. We would just call it methanamide. We drop the E of methane and we add amide. So it would still be the same beginning. It would still be N,N-dimethyl, but it would be N,N-dimethylmethanamide rather than N,N-dimethylformamide. Okay, and let's try an example here. We have a lot going on. Let's identify the highest priority functional group and let that set our, which one will be our carbon chain, our parent chain. And right here, this is the carbon that's most important because that has the carbonyl and the nitrogen. Okay, so that's going to be our parent chain, is the longest carbon chain from that point on. From that point on, so this is 1 carbon, 2, 3, 4. This is a 4-carbon chain. So what's that going to be called? Looks like a butanamide. Butane derivative. And now butamide. Butanamide means that I have an amide at carbon 1. Carbonyl plus a nitrogen. Okay, now what else do we have here? We have an N-ethyl. A lot of times the N substituent is listed all the way out in front of the molecule before the carbon substituents. Sometimes they're mixed in. It maybe depends on the publisher. Okay, so this is called an N-ethyl because it's an ethyl group on the nitrogen. And what is this group called? What is that group called? Well, if you could use common names, there would be a simple name for this. Looks like the isopropyl group with an oxygen. So we could call this an isopropoxy. We could call it an isopropoxy, but that's not IUPAC. So let's figure out an IUPAC name for this substituent. Remember, the point of attachment has to be carbon 1. So this is a 2-carbon chain. This is actually an ethyl group, but it has a methyl at carbon 1, so it's a 1-methyl ethyl is how we call an isopropyl group. But it's also has the oxygen here, so we're going to call this 1-methyl ethoxy. So it's actually an ethoxy group. Here's the ethoxy, but it's a derivative of that because at the one carbon it has an extra methyl. So this is called a 1-methyl ethoxy. Okay, and like I said, usually the N substituent comes first. Turns out that's also alphabetically correct, so we're in luck here. So this is N-ethyl is listed first. And then at position 2, we have this big whole group, 2, and then parentheses to keep it all together, a 1-methyl ethoxy. So our nomenclature rules are building on one another bit by bit so we can eventually, name some pretty complex molecules. Okay, and finally, let's take a look at a nitrile. A nitrile is RCN, so we have that CN triple bond group. That is also a carboxylic acid derivative. Okay, and so it also indicates that the first carbon, the carbon of the nitrile defines the beginning of the carbon chain, just like the carboxylic acid derivatives. I typically don't bother trying to distinguish who has a higher priority among the carboxylic acid derivatives. So, assuming you have just one of those, that's going to be higher priority than any other functional group we saw. But if you want to get into the details of how do they rank amongst each other, you can look that up and have those challenging problems. Okay, so we're going to find our longest carbon chain, and then we're going to not even drop the E of our alkane name. We're just going to add the word nitrile. So that must be the simplest suffix to remember, because you don't even have to drop the E. You just stick the word nitrile in the end, and that magically turns your carbon chain into a nitrile instead. Now this is kind of a tricky one to recognize. This molecule's common name is acetonitrile, but you can see that it is the two, just like, remember this was the acetyl group, so it's the 2-carbon derivative that we had all these names for. Acetone, acetic anhydride, acetic acid, acetamide, etc. So the 2-carbon nitrile is called acetonitrile. Okay, so again, even though it looks quite different from the others, this is a common name. Another very common solvent to use in organic chemistry, so you might see acetonitrile around. Okay, but what would the IUPAC name be for acetonitrile? Well, our longest carbon chain is right here. It's just a 2-carbon chain, and so that's an ethane derivative. So he's called ethane nitrile, and that's it. You just add the word nitrile to the end, ethane nitrile. Notice that the cyano group is part of the carbon chain. So that's important here. You might, at first glance at the way this is drawn, you might think that your parent's down here and then you have some kind of cyano group attached, okay? Well, it would be called a cyano group if we had some higher priority functional group here, but we don't. The cyano group is the highest priority functional group, so that's actually part of our parent. So our carbon chain has to start right here, and from that point our longest carbon chain goes in either direction because it's symmetrical, but this must be our parent. So 1, 2, 3, 4, 5. This is actually a pentane derivative. We're going to call that pentane nitrile. And what do we have attached? We've got some methyl groups, and then we have another one of these complex substituents. Let's see if we can tackle that. How do we start? Well, we look at the point of attachment to the parent. We define that as carbon number 1, and then we number from there. What's the longest carbon chain starting from that point? The longest carbon chain would be 1, 2, 3. Doesn't matter if you number up here or down here, 1, 2, 3. So this is actually a propyl group. It's a propyl group, but that does not, it's not just a propyl group. It's got a methyl at carbon 1 and a methyl at carbon 2. So what are we going to call this? We're going to call this a 1,2 dimethyl propyl. It's a 1,2 dimethyl propyl. We're going to put that whole big thing in parentheses because it's all one group that's attached to the parent, and it's attached to the parent at carbon 2. So it's called a 1,2 dimethyl propyl. And I listed that last, I listed that second because the other groups we have are methyl groups, and methyl comes before methyl propyl. Remember, we ignore the di for alphabetizing, but methyl comes before methyl propyl because methyl propyl is all one word. And so at 3 we have a methyl, and 4 we have a methyl, so we're going to call that a 3,4 dimethyl. make sure you give yourself plenty of room when you're doing these nomenclature problems because the names can get really big and long. And make sure you draw your letters nice and large and clearly so that there's no mistaking an E for an A or an O because as you can see, that makes all the difference in getting these problems correct. Okay, let's do this last one. This looks like a doozy, doesn't it? Okay, we have an aldehyde, we have a ketone, we have an alkene, we have a nitrile. Which of these groups wins? Remember, it's based on the oxidation number, so any carbon with 3 bonds to oxygen or 2 heteroatoms is going to win. And so this is our highest priority functional group, so he gets it will be named as a nitrile. All the other groups are just substituents attached to the parent because we can only have one suffix. So let's include that nitrogen in our parent so we make sure that we've already accounted for it. 1, 2, 3, 4, 5, 6, 7. So 7 carbon chain is heptane. Double bond makes it heptene, so we have a 2-heptene. 2-heptene. And how do we make this a nitrile? We just add the word nitrile to the end. So that means the first carbon of that 7 carbon chain is part of a carbon-nitrogen triple bond. So we have 2-heptene nitrile. Now what do we have at carbon 4? Okay, remember we would name it as a ketone if we didn't, that was the highest priority functional group. And then we would use the ONE suffix, okay? But now it's a substituent. He's not called a keto group. That's a really common mistake. Instead, he's called an oxo group. Any carbonyl is called an oxo substituent. We have an oxo at 4, and we have an oxo at 7. So again, now an aldehyde or a ketone, they're both the same thing. They're just carbonyl substituents. And so we're going to call this a 4,7 dioxo. Just like we would have a dimethyl or a dichloro or diphenyl, this is called a dioxo. Excellent. And that accounts for our function group, but there's one last thing that's missing here. Is there any stereochemistry that might be relevant? Look at this double bond. How would you describe that stereochemistry? Both of these groups are pointing in the same direction on the same side. So yeah, actually the cis isomer has been shown here, so we need to show that. Okay, it's okay to just call it cis here because you have only 2 groups. It's also okay to call it Z. It's never wrong to use the E and Z nomenclature. If you want to get used to doing that, then that's a good idea. Z means these 2 groups are on this same side. In fact, in some cases, sometimes you'll learn that unless you have 2 identical groups, they prefer not to use cis but to use Z instead. But if you have 2 hydrogens, it's quite unambiguous if you call it cis. So that's widely accepted as an okay name as well. So that wraps it up for all the different functional groups that we're going to learn the nomenclature for. I realize nomenclature is not the most fascinating topic in the world, but just like you have to memorize the alphabet before you can learn how to spell and learn how to put words together, you do need to memorize these nomenclature rules. It's one of the few things in organic chemistry that really you do have to memorize, you do have to know the names because we need to be able to communicate. And if every time you see one of these IUPAC names, it's a huge roadblock for you and you're going to have to spend 10 minutes figuring out what it means, that's going to be very costly. So it's worth to maybe put together some flashcards and start to get familiar with these. Of course, the more problems you work on, the better you're going to get at, and the more it's going to be second nature to you, just like the alphabet is now that you've had plenty of time to practice that. So I hope to see you again soon. Thanks for coming.